Hello, everyone. Thank you for attending ChipEx 2021. Hope you're all staying safe. And I'm sorry that I'm unable to make it live to see you, hopefully in the near future. So today, my name is Deepu Talla. I'm working at NVIDIA. And I'm going to be talking about AI technologies for edge computing. I've been in the semiconductor chip industry for 20 years. Actually, it turns out this is my 20th anniversary after I graduated with a PhD in computer engineering. And I've been working with chips and systems for, of course, all my 20 years. So I'd like to share with you what is going on in the area of edge computing and how AI is impacting computing today. So if you think about computing, most of you, of course, are familiar with cloud computing, and especially in the last 5 years or so, we've seen the explosion of AI and the impact in cloud computing, whether it is for microprocessors to accelerators like GPUs to networking and data processing units as well, and storage. Cloud computing has exploded, so we all know that. Now, at the other extreme, if you look at the left part of the slide, IoT is a pretty popular, IoT devices are pretty popular. And most people, when we talk about edge computing, they associate that with IoT. And today there are probably around 50 to 60 billion IoT devices that ship every year. And in the future, there might be a trillion IoT devices. However, there's two other edge computing technologies that are emerging very rapidly. One, if you look at in the middle of the picture, is this edge data centers, whether it's edge servers or some people call them appliances or gateways. So this is about bringing some of the cloud technologies close to the point of action, point of where the data is captured, and that is exploding. And that's typically referred to as edge AI in the industry today. And that's probably a few million servers or units that are shipping today, and the future we expect those to go 10 times higher, maybe hundreds of millions of systems that will ship in that space. And then secondly, the other emerging area is autonomous machines. So because AI, what it used to be, in the last few years, the explosion of AI in the cloud, now AI is coming from just being exclusive in the cloud to the edge. And autonomous machines is one of the main reasons for that. So autonomous machines is essentially these robots. If you think about a delivery robot, if you think about a service robot or an industrial manufacturing arm or a retail store that has multiple cameras that are being analyzed for foot traffic or social distancing and so on. So you can imagine all of these things, AI is coming rapidly into that. So these end up making decisions real time at the point of action. So that's a new class of device. Today, very small number of units that are autonomous, of course, probably a few million. But in the future, we can expect to see billions of autonomous machines. So today in my talk, I'm going to be primarily focused on edge computing and how how I see that being transformed in the next coming few years. So the most important thing when you think about computing is to think about a full computing stack. My background is computer architecture. So of course, I spent a lot of time on architecture, processors, hardware. That's super important. However, that is necessary but not sufficient. And I'm going to show it to you in this presentation, how much at NVIDIA we are actually, pioneering the aspect of the full computing stack, which means that it's not just about the processor and the architecture, but also how much you make investment into software, whether it's tools and libraries or application frameworks. So this is what I'm going to be talking about, these three aspects of the computing stack in my talk today. So the first thing about computing architecture, when you think about AI and edge processing, 5 years ago, the wisdom was that most of the edge AI would be fairly simple. We all thought that around 2015, 2016, it's mostly going to be convolution neural networks. It's going to be object detection and object classification. And that's pretty much it. Well, it's turning out that it's not that anymore. AI edge inferencing is turning out to be super complicated because of the new species of networks that are coming on board, new capability that's coming on. So convolution neural networks, of course, are important. However, transformers are becoming very, very important, especially in the area of natural language processing, speech, right? So when you're doing all this natural language understanding, whether it's a car, whether it's a service robot, whether it's in a drive-through, you need to make all this processing happen instantaneously. And so new neural networks in the form of transformers are coming up. Reinforcement learning is becoming increasingly popular, especially in robots, industrial arms, if you will, that need to make real-time decision. As in the future, we expect them to be, operating alongside humans. So we need to make sure that these robots are safe, and the neural networks there would be, reinforcement learning is a popular topic. So then you see, additional neural networks. So the result of all of this is 5 years ago, when people were thinking about edge and AI inference, it was thought that it's going to be fairly simple, but it's turning out it's actually not that trivial anymore. So you need to make sure that whatever architecture you're designing for, it needs to be able to handle all of these, the complex neural networks that are being invented every day. So if you think about what are the best ways to accelerate, AI inference workloads, of course, at NVIDIA, we've been pioneering GPUs, making those, the GPUs that were originally designed for gaming and graphics. We've enhanced them to be general purpose, so GPU. And we are now in our third generation of our GPU with Tensor Core, which essentially Tensor Core is what it does, adding those specialized instructions to the GPU to accelerate artificial intelligence. And I'm not going to be covering a lot of detail about Tensor Core GPUs in this talk, because there's a lot of literature out there. You can read about our Ampere GPUs and how we've architected those GPUs to be able to essentially accelerate AI inference and be very programmable, so that we can basically support all of these neural networks. So that's how we at NVIDIA have been focused addressing this problem. The second one, deep learning accelerators are super popular, of course. Even at NVIDIA, we've been working on this for since the beginning, and we even open sourced a version of a deep learning accelerator called NVIDIA 4 years ago. And this is increasingly popular, especially in edge computing, especially in IoT devices where you are super constrained by power and size and cost. So with that, you can tend to be more fixed function, if you will, as opposed to be fairly general purpose. So deep learning accelerators are great for super low power, low cost, but at the expense of programmability. So deep learning accelerators are very, very popular in IoT. CPU ISA extensions, you've seen that. It makes sense because every computing system has a CPU. It makes sense logically to add ISA extensions to accelerate AI, just like 15, 20 years ago, we've added SIMD instructions for accelerating multimedia and video and audio. Now it's natural that you add all these extensions to the ISA. DSPs, of course, DSPs are very popular in embedded and mobile type of SoCs, and natural that if you already have a DSP, why don't you use the DSP to accelerate AI inference? FPGAs are, of course, trying to address this problem as well, and it's one of the interesting approaches to solve that. And then recently, we've seen this CGRA, which is basically coarse-grained, reconfigurable architectures. So the idea here is that, because of the challenges of AI and new networks being invented all the time, and you need a good amount of programmability. So CGRS are one ways to effectively do it. So these are all different techniques that can be, that are being used, and there's a lot of work that's being done in all of these areas to accelerate edge computing and AI inference. So I'd like to leave you with one thing. If you are a chip designer, if you are working on any of these accelerators, obviously, what is the performance that you get? So MLPerf is the best proxy we have today for measuring AI performance, both for training and inference. In the area of inference, MLPerf does both edge inference and also cloud inference. And recently, a couple of months ago, this was done, the latest version of MLPerf. And NVIDIA, as you can imagine, because we use our Tensor Core GPU, we are able to basically run every network that's possible because of the flexibility of that. And then again, we'll provide the slides. You can study that. So, but if you're a chip designer, you should pay attention to this, because this is one of the best benchmark set that we have that essentially dedicates and towards measuring machine learning performance. So that's the first step. So doing the chip, having a great computing architecture is, of course, very important. However, that is not sufficient. The next thing that we need to do is to have great tools and libraries. This is where a lot of startups, a lot of companies have trouble because they have a great computing architecture, but if you don't have the associated tools and libraries, it's very hard for users to adopt your platform. So I'm going to give you some examples. At NVIDIA, we've been spending enormous amount of energy in creating all these tools and libraries. I'm going to give you just a flavor of a few that we focused on. The first one that we do is what's called cuDNN. Essentially, you have many of these frameworks from PyTorch to TensorFlow and others that you need to be able to run very efficiently on your computing architecture. So you need to provide a library. It's very hard for expecting expecting somebody in developing a framework to go and optimize to your architecture natively. So you need to provide this. So at NVIDIA, we provide this cuDNN tool that's widely used. So if you're designing a computing architecture, make sure you build an appropriate library that accelerates all of the machine learning tasks. The next thing that we've done is a deep learning inferencing compiler. We call it NVIDIA TensorRT. Essentially, there's two parts of it. The first one is machine independent, essentially taking a network that comes out of a framework and then optimizing, creating a plan. And then secondly, a machine dependent optimization, depending on how many cores you have, depending on the precision, depending on all of that, you have to optimize it for the target machine. So you have to invest in making sure that the optimizing compiler essentially takes the network that's coming out of the framework, and then it's running efficiently on your target architecture. And then this is a fairly important piece. If you think about AI model today, the biggest challenge in AI models today is, okay, this model, so it's fine. There's a lot of examples there. However, the amount of time it takes for an engineer or a developer to take an AI model and basically bring it to production is enormous. Number one, because you have to basically start annotating data and training that. That takes an enormous amount of time. I mean, literally, to collect the amount of data that you need to and label it and then train it. And so if you want to start from Model Zoo or something, it's an okay start, but it's actually not a high performance model. It's not really optimized for a commercial data set. It might be okay for a research data set, but it's not optimized for a commercial data set. So essentially what's happening is, if you start with Model Zoo, you're really starting at, if you want to go from 0 to 100, you're really starting at probably 10 or 20, but you want to start with something like 80 or 90 to get to 100. So what we've done at NVIDIA is we have invested a lot into creating these pre-trained models. Right now, I'm showing examples for both computer vision and conversational AI. And we actually have collected a lot of data, real data, commercial data, with the right ethical treatment, with the right the right to be able to use it, and essentially we've experimented, we've labeled all of the data, we've trained it and created a pre-trained model, and then we give you that pre-trained model, which is a very good starting point. So it's at approximately 80 or 90 if you want to reach to 100, and then we give you all the tools. Here we give you a tool called a transfer learning toolkit and a Talla toolkit, which is train, adapt, and optimize. So essentially, instead of you collecting 1 million images, for example, we've already done that. You collect, let's say, 1,000 more images for your specific task, and then you retrain the network, and you use this tool to completely optimize it, automate it, and then you can, basically create a custom model for yourself. So we've invested in this. So this is one example I'm going to show you. And by the way, all of this is publicly available to anybody. If you go to the NVIDIA website, you can download these models. And I'm showing you here, it's a pretty busy slide, but I just wanted to show you a sense for, at the bottom of the slide, you see the different platforms from NVIDIA, from a Jetson Nano, which is starts at a $59 computer, all the way to a T4 GPU, which is a data center GPU. So the same model runs across multiple platforms. And then, we provide the model, and then you can download the model and you can adapt it to your domain. Okay, so that's very important. So you have to provide tools and libraries in order for a developer or user to adopt your architecture. That's great. Still, there's another missing aspect that is important. That is applications and frameworks. And let me talk briefly about that. The first thing that's important when you think about edge computing is, traditionally when people think about edge computing, they think of embedded computing. Embedded computing historically has been, you basically program, the machine one time and you deploy it and that's it, right? You rarely have to upgrade the software. I mean, you think about your refrigerator, think about your, washing machine, think about any of those things, whatever software it comes with for the rest of its life, it's going to be the same software. However, with new cloud technologies coming in, with mobile technologies, if you think about your phone, your Android's updated every year, and then your apps on Android are updated periodically. So, and then the cloud, it's your recommendations, your Netflix recommendations, or your advertisements, all of them are constantly improving because it's happening real time in the background. That's what's expected in edge computing. So, which means edge computers need to be cloud native. So the containerization, the flexibility to adopt, all the cloud technologies is super important. So essentially, now this is about bringing some of the best practices of cloud computing to edge. So cloud native is an important aspect, number one. So at NVIDIA, we have been focused on multiple application frameworks for different domains, because you have now the moment when you're trying to create an application, you have to get more specialized for a specific domain. You can't just be general purpose. So here I show you examples of 6 application frameworks at NVIDIA that we are focused on for edge AI. Metropolis is for video analytics, for smart cities and retail analytics. Isaac is for robotics. So we create a simulation platform. We create a hardware simulation in the loop, software in the loop. Drive is our platform application framework for self-driving cars. Again, simulation and real-time training, and then hardware in the loop. Clara is for medical imaging. Jarvis is our framework for conversational AI. So we have models for natural language understanding and ASR, speech recognition, and text-to-speech. So all of this. And then Ariel is our computing stack for framework for 5G, as we're increasingly finding 5G coming into being disaggregated and not just being centralized, but running locally on a server, for example. So I'll just show you quickly one example. When you think about AI and edge computing, it's natural to think that it's all about AI inference. The answer, actually, the truth is, it's not all about AI inferencing. Of course, AI inferencing is one of the most important things, but you all know, as computer architects, Amdahl's law, if you increasingly speed up AI inferencing, the rest of the system bottlenecks will catch up, right? So it's important not just to do AI inferencing right, but actually it turns out that there's a lot of pre-processing and post-processing that you need to do around the data. If you don't speed that up, you can speed up your AI inferencing infinite, but it turns out that your total speed up will be no more than 2 or 3x, because the rest of the pre-processing and other examples, really will dominate. So make sure that you are accelerating the whole application end to end. So it's just one example of how we've done it in the case of our deep stream, which is for Metropolis platform. If you think about camera processing, you have to process the camera, you got to decode camera, you got to do image processing. Sometimes it's a 360 camera, you have to dewarp it, you have to resize it, and then you do an AI processing. But once you do your AI processing, you need to do tracking across cameras in time and space, and you need to visualize that data. So all of these steps need to be accelerated. Otherwise, you will not get the end-to-end application speed up. Okay, and then my last slide before I wrap up. These edge devices need to be managed. So at NVIDIA, we're building something called a fleet command. Of course, you can, there's other options as well. This is about managing all the devices in the field from the cloud. So you need to have a platform that's managing all of these devices. So I'd like to summarize my talk with how we are solving the challenge of edge AI. Number one, you need to have great computing architectures. AI inference is increasing complexity and diversity. So make sure you have the flexibility. Number two, it's not about just the AI itself. You need to accelerate the full stack. Otherwise, Amdahl's law will bite us. And number three, these AI products, when they're deployed at the edge, are going to be in the field not for 1 or 2 years, but maybe for 5 or 10 years. And the consumers and the customers expect you to update and improve the AI. So you need to make sure that the product life cycle is maintained. So with that, I'd like to thank you for taking the time to listen to my talk. And again, I apologize for not being physically present there. Hopefully in the near future, I get to see all of you. Thank you.